Previously, we talked about the derivation process of the equations to determine the longitudinal reinforcement resisting torsional force in a member. The derivations is on the basis of an imaginary truss model made of the steel reinforcement as well as the compressive strut of the concrete. Through trigonometry derivations, a relationship between the shear force and the force in the steel bar is determined. By substituting the relevant formula, the equations for the longitudinal reinforcement bar is obtained. In this videos, we're going to proceed with the derivations for the torsional link. We're going to use the same imaginary truss model. Just that our focus now, it will be on the link. The diagram here shows the cross-sectional view where a box section is assumed. This represents the side view of the member. We are referring to this part. You have the longitudinal bar, the link, and also the compressive strut. The equations for the torsional link, it will be derived on the basis of this diagram. The equation here represents the comparison between the strength provided by the link and the vertical force acting on the model. Assuming that this vertical force, which is in the tension, is fully taken by the link. Bear in mind that this diagram represents one side of the member. By looking at the arrangements of the link, we are referring to one leg of the link. This is slightly different from the calculations of the vertical shear reinforcement, where the area involved is due to the two legs of the shear link. Try not to get confused with the area of the link that you use for the torsional design. To make it simple, torsional design, the area refers to one leg. Shear resistant design, the area refers to both legs. Coming back to this, we want to determine the tensile force of the torsional link. This is calculated by having the area multiplied with the design yield strength, assuming that at the ultimate state, the torsional link would have yield. And don't forget the partial factor of safety for the steel, which is equals to 1.15. And then on the other side, it will be the force acting in this direction. First, you need to understand the diagram here. You have a shear flow here. Since we are designing on this side, the shear force acting here, it will be equals to the shear flow, which is the shear force per unit length, multiplied with the h. Now, if you see the dimension h here, it is not the gross height because we are referring to an equivalent box section model. The h that we are referring to is actually the h minus the effective thickness, which is this. The diagram here already shows to us it is referring to the center line of the effective thickness. By having the shear flow multiply the height, you get the shear force here. Theoretically, your shear link should have to resist the shear force here. However, since the torsional links are spaced out at a consistent spacing, this forms a truss model here due to the interactions between the longitudinal bar, the link, as well as the compressive strut. Then you will need to do some slight conversion. First, you look at the torsional link. There is an angle here for the compressive strut. Let's say this angle is equals to a theta. Draw two parallel lines along the angle, and this will represent the compressive strut of the model. Draw a vertical line. This distance represents the h, and this angle represents the theta due to the trigonometry conversion. Now, in order for you to get a compressive force, you are looking at the force acting in these directions instead of this direction. Therefore, you will need to get an imaginary plane here. How do you get this? Since you know the theta is here, and this is the Pythagoras. Cos theta, it will be equals to this divided by this. We arrange the formula. This side, it will be equals to h multiply cos theta. This is how you get the h cos theta. That means whichever the angle of the compressive strut, the horizontal component here, it will represent the h cos theta. And this distance represents the Pythagoras, which is the h. It may seem complicated, but this is pure conversions in terms of the trigonometry. You can try by yourself, taking this as an angle, which is the same angle here, and then you play around with the dimensions. Now, having this h cos theta set, we're going to look into this ratio. Depending on the magnitude of this torsional force, the angle of the compressive strut changes. The larger the magnitude, the larger the angle. Now, if the torsional link is spaced at the exactly the what it is happening in the actual member, that means the tensile force provided by the torsional link shall be equals to the Q times H, which is this force. But in the actual circumstances, once the torsional link is placed within the member, it is fixed. The torsional force can be variable. It may not always be of the same distance of the h cos the angle. So what you're going to do here is you need to do some simple conversion, assuming the influence of the forces in the torsional link is actually proportional to the ratio between the spacing and also h cos theta. With that, this establishes the formulas for the torsional link. Now, if you rearrange the formula, at the same time substitute this formula into here, you will get this formula. Where do you get this? This one we have discussed in our previous video, which is this formula. Now, how do you obtain the AK? That one we also mentioned in our previous videos. How do we get the AK? And also the effective thickness under different circumstances. With that, we have obtained the formulas for the link. Now, bear in mind that try not to get confused with the design for the shear link. For the torsional design, we are talking about the area of the link referring to one leg instead of two legs. And then due to the spacing of the link at a distance of s apart, the force within the link, it will reduce proportionally. That's why we need to get the ratio here in order to estimate the remaining force to be taken by the torsional link. One more thing is that we have the longitudinal reinforcement for torsional. We have also torsional link. This reinforcement for torsional resistance shall be added on top of the full bending and the shear reinforcement required. That means whichever amount that you have calculated as required from the longitudinal reinforcement due to the bending resistance, and then you have also calculated a certain amount of the longitudinal reinforcement for the torsional resistance. Now, the final area of the reinforcement to be provided, it will be the summations of the two, with the assumption the area for the bending is fully taken due to the flexural bending, and the additional area it will be for the torsional resistance. They are not overlapping each other. Same principles applies. Now, if you have calculated certain amount of the shear reinforcement as a shear link, the shear link can be at the same time being used as the torsional link. However, the amount required for the torsional resistance will have to be added up to the shear link. The purpose here is to cater the situations where the member is subjected to the full shear load and at the same time is also subjected to the full torsional force. That's why the torsional reinforcement is to be added up to the full bending and the shear reinforcement required. And this can be done by increasing the size of the bar or adding more bars in the section.